Okay, well, everybody say hi.
Hi.
Hi, Jennifer and Clara. Sorry that you can't be with us. We are going to be talking today about an important use of the mean value theorem, and you might call that derivative jeopardy, but we're really going to call it antiderivatives. But before we get there, do you have any questions about Yes, sir.
How was it? Class yesterday.
Uh-huh.
I want to know about the difference between the
And the intermediate value theorem? Okay, yes. So just to review our three existence theorems that we have so far. The intermediate value theorem has as its condition that f of x is continuous on the closed and bounded interval a to b. And when f meets that condition, and we can draw a picture here, a, b, here's my continuous function f. If f is continuous on the closed bounded interval a to b, then f takes on every value between f of a and f of b. So if I come over to here and identify f of a right here on the y-axis and f of b right here, and I pick any value in between, call it L right there, then what the IDT guarantees is that my curve will intersect the line y equals L somewhere. Could be one, could be many. You know, it's a sine function with infinite number of times, right? So that's the intermediate value theorem. The extreme value theorem, if f of x is continuous on the closed bounded interval a to b, then f of x has an absolute max and an absolute min on a to b. And so looking at our same function that we have right here, we can see that f has an absolute max, it has an absolute min value. And then finally, the mean value theorem adds an additional condition. If f is continuous on the closed bounded interval a to b, and also differentiable the open interval, then there is a c between a and b such that the slope of the tangent line is equal to the slope of the c. Yeah. And the picture here, where I have a function that is continuous and is differentiable, and the right-hand side of that equation, f of b minus f of a is the slope of that line, and the mean value theorem is guaranteeing at least one point, could be more, where the tangent line is going to be parallel to that secant line. So you can see that this is not at all like the intermediate value theorem.
so that the when I there's no related to IDT.
Correct. That's right. It was just a review. Right. It was all mean value theorem stuff. Yeah. I'm just reviewing it because these are the three existence theorems that we've had. We'll have a fourth by the end of the year. And so I just wanted you to have those fresh in your mind. Okay? All right. Well, let's then actually use the mean value theorem in an important way. And I'm going to review very briefly our theorem, a theorem from the end of yesterday. And that theorem is, if f prime of x equals 0 on the interval a to b, then f of x is a constant c on that interval. And the reason for this is, the easiest way to put this is that if f is not constant, if it has a bump somewhere, then because it has a bump, it will have a non-zero average rate of change, and because it has a non-zero average rate of change, it will have a non-zero instantaneous rate of change somewhere in this interval, and it doesn't. So it cannot possibly have a bump because it cannot possibly have a non-zero rate of change. So that's the spirit of that theorem. If you want the whole details, you can go back to the notes from this week. Now we're going to leverage this to answer a really profound question. And to get at that question, I want all of you to come up with a solution to this problem. If f prime of x equals 2x, what is f of x? Go ahead and write down your answer. What do you have?
F of x equals x squared.
Okay. Mark, what do you have?
Same.
Same thing? Okay. In my other class, we had some variations on this. We had one person who gave you x squared minus 2. Oh, that works. And we could have x squared plus 12. Somebody really of interest gave me x squared plus 10,000. That also works. And then I started getting silly. And had x squared plus e to the square root of the sine of pi over 3.
That's all it is.
That's right. This is a constant. That's exactly right. So all of these are actually answers to this question. And in general, I could say that f of x equals x squared plus any constant c would be an answer to this question. But now I have a really profound question. Could there be others? Could there be some function that is not in the form x squared plus c, whose derivative is nevertheless 2x? Could that be possible? That's an interesting question. What's that? Yes. The question is, could there be others? Could there be some g of x that is not x squared plus a constant, whose derivative is nevertheless 2x? Ooh, that's an interesting question. And it turns out the answer is no. And here's why. Let's suppose that there is. Suppose I have some other function g so that g prime of x is equal to 2x. Then let me subtract f from g. And we'll call it h. Actually, let me write it as g minus f. Okay? And let's find the derivative of h, which of course is g prime minus f prime. But g prime is 2x by hypothesis, and so is f prime, so that when I subtract g prime minus f prime, I get 0 for every single value of x. But because h prime is 0 for all x's, therefore h of x is a constant. And that means that g of x and f of x differ by a constant as well. In other words, what I'm saying is that any function whose derivative is 2x must be equal to f of x equals x squared plus a constant. There are no other such functions. Let's generalize that and do a proof. So here is our theorem for today. two functions have the same derivative on the closed interval a to b, then they are the same function within an additive constant on the interval a to b. Two functions with the same derivative are the same function within a constant. And our proof is going to look just like what we did a moment ago. We're going to create a helper function, which is the difference between f and g. And we're going to take the derivative of h, and when we do, we get f prime plus g prime. But because f prime equals g prime, therefore f prime minus g prime is 0, so that the derivative of h is 0 on the entire interval a to b, which means that h of x must be a constant on that entire interval a to b. And since h of x is equal to f minus g, therefore we conclude that f of x is simply equal to g of x plus a constant, as advertised. Now here's the upshot, the real significance of this, and that is that if I give you the derivative to some function, then at least in theory, there is a unique function within an additive constant whose derivative it is. If I give you the derivative of some function, then there is a unique function whose derivative it is. If I ask you, what is the function whose derivative is 3x squared, the answer is x cubed plus a constant. There are no others. If I ask, what is the function whose derivative is secant squared x, the answer is tan x plus a constant. There are no others. Does that make sense? So this leads to what I sometimes call derivative jeopardy, but we really are going to give it its official name, antiderivatives. And the question is usually posed like this: find a function whose derivative is f of x.
Is there a definition?
What's that?
Is there a definition?
Yes. Yep. The antiderivative of f is the function whose derivative is f.
Keeps the voice.
Right. And this is the question that the antiderivative is trying to solve. We're going to have a bit of notation for our antiderivatives. The way that we are going to notate the antiderivative is with this symbol right here.
The function whose derivative is f of x? Oh, okay.
Yep. The function whose derivative is f of x. So this is going to be the notation that we are going to use for the antiderivative of f. Sometimes that's pronounced an integral sign, so you might hear that referred to as an indefinite integral, but we're just going to call it antiderivative. And this is the function whose derivative is f. So if we were to express this, the previous problem that we talked about in antiderivative notation, we would say that the antiderivative of 2x dx is equal to x squared plus c. And the reason for that can be found simply by checking. When I take the derivative of x squared plus c, what I get is 2x, which is identical to the original. We call that the integrand. And because this function has the same derivative as the original, it must be the function that we are seeking. Because two functions with the same derivative are the same function within a constant. Yes? Ah, good question. Could we have different variables in there? At this level, no. Later on, we're going to do, we might consider the possibility of doing some substitution or something like that, but for now, the variable must be what it is. Okay? Good question. Okay, so let's do a little bit of practicing with this. Antiderivatives are going to be different from derivatives in that instead of following a series of mechanical rules, for the antiderivatives, we are going to have to recognize derivatives when we see them. We're going to have to know those derivative rules. So, for example, what is the function whose derivative is cosine x? Plus the mandatory constants. Now the plus c here means that I have the general answer. This is the most complete possible answer. So this is the general antiderivative. Or, what if I asked you for the antiderivative of 1 over 2 root x? That's right. Plus c. This constant here is mandatory.
So there's no way to find the c value.
That's a great question. We're going to address that at the end of class today, which is, can we say anything additional about the value of c? At this time, we cannot, but we will in a little bit. Or, suppose I did, here's a tricky one. The antiderivative of 1 over 1 plus x squared. A function whose derivative is 1 over 1 plus x squared. What is that function? You got it? Almost? I'll teach you that. No. Function whose derivative is 1 over 1 plus x squared. If you're not sure, you can go hunting through your list of derivative rules in the book. You do have a handy list of derivative rules somewhere, right? Grab it. Got one more to go. keep going. Keep going. Up and down. So the fact that we're struggling with this indicates something important, and that is that those derivative rules have to be on the tip of our tongue, right? This guy is actually inverse tangent. Yep, exactly. Okay, so here's the important point that I want to make about our antiderivatives. And that is that finding antiderivatives is going to be a matter of knowing the derivative rules well, that's first thing. And second of all, it is going to be much more like solving a puzzle than it is going to be following a bunch of rules. Does that make sense? We will have some antiderivative rules, but generally speaking, we're going to rely on our puzzle solving ability. Okay. Now, let's consider this one. Speaking of puzzle solving ability, I'd like for you guys to take a stab at finding this and then check your result. And when you check your result, it might help you refine your answer. I failed back over here because I failed to have us check. We should have checked each one of these guys. And when we check our antiderivatives, we check them by taking a derivative of the result and verifying that our derivative is in fact correct. And we actually want to check every single time. And there's a simple reason for that. The reason we want to check every single time is that our derivatives are much better than our antiderivatives because we've been doing them since October. And because of that, that means that I am much more likely to catch my mistakes if I check by taking the derivative. All right, so I'd like for you guys to do the same kind of thing. Take a stab at what you think that might be, and check it by taking a derivative, and then see if you can fix it. So I'll let you do that. If you're following along at home, go ahead and try to find the antiderivative of x cubed, and we'll be back in a moment. Okay, let's see what we can do here. What's your first attempt?
Well, x to the fourth, you get EN with x to the fourth. Okay.
So if I try x to the fourth plus c and
Yeah.
reverse this, then when I check it, the derivative of x to the fourth is 4x cubed. Well, that's pretty close, right? That's pretty close. So could I modify this function in some way so that when I take the derivative, my 4 cancels out? Try it. And using the constant multiple rule, I get 1/4 of 4x cubed, and that's it. That's exactly what we want. So we get 1/4 of x to the fourth plus c. And we did that by reverse engineering our process. Now we'll have some smarter ways to do this starting tomorrow, but for now you can sort of see how this might happen. Now, let's talk a little bit about the principle of algebra first. Suppose I want the antiderivative of something like this. Okay. We would be foolish to just try to take the antiderivative of the top and bottom and divide them. That's clearly not going to work because when I take the derivative and check, I have to do quotient rule and something. Okay. So get that out of your mind. Instead, consider, could I use some algebra to rewrite this and make it easier to work with? I think I can. because division is the same as multiplying by the reciprocal, I can rewrite the integrand as x squared plus 1 is 1 over x. Distribute. And get the integral of x plus 1 over x dx. And now I consider the function, let's see, what's the function whose derivative is x? Good. And what's the function whose derivative is 1 over x? What's that? You said limit, but what is that really? What's it really called? What's the function whose derivative is 1 over x?
Oh, x2 and x3.
Nope. We have a function whose derivative is 1 over x. What is it?
But you, no.
Oh my goodness. The derivative rules have drained out your brain. Ah, happens every year around this time. Oh, wow. I will say to your shame that the other class had this one. It is the natural log of x. Yep. Yep, here it is. Now check it. Because of our sum rule for derivatives, we can go term at a time. And when we do, we get something that we can recombine with common denominators. And so that equals the original integrand, and we're good. Yes, sir.
There's no way to get 1 over x from the other.
From a power, right, there is no way to do that. We'll actually see that tomorrow. Yeah. And also, we can rely on our theorem, right? So if there were some other way to get a function whose derivative is 1 over x, that function would have to be natural log x plus c. Because two functions with the same derivative are the same function. Now, what I'd like to do is to consider some homework problems in your book. And I want to start with this problem. On page 203, problem number 32. Actually, let's do 30. We've already kind of done 32. And the directions are find all possible functions that satisfy. And then here, number 30, we are told that f prime of x is equal to 2. I'd like for you to observe how this problem is stated. We're trying to find a function, and the condition on that function is that we know its derivative. That's derivative jeopardy. And so we're going to begin with a representation of our function. And the representation of our function is that f of x is equal to the antiderivative of the given quantity. Huh? And then we'll go ahead and give a solution. What is the function whose derivative is 2? Plus c. And we are not going to forget that mandatory constant c. Yes, you should definitely check it. Now, I like this problem because it says something really profound. Take a look. It is saying that the function that has a constant slope of 2 is a linear function. Isn't that nice? That makes a whole lot of sense. Now, let's consider number 36 on the same page. And here's where we are going to address your question about finding the constant. On number 36, we are told that f prime is equal to 1 over 4 x to the 3/4 power. And we are also told that our function passes through a particular point, passes through the point 1 comma negative 2. This is number 36, I believe. And so they want us to find f that satisfies these conditions. So we begin with our representation. F of x equals the antiderivative of the derivative. And just as we did a couple of problems back, let's do a little bit of algebra first to try to get some inspiration. Because having that x to the 3/4 in the denominator there was just not going to be helpful. And so now I look at this and I wonder, can I find a function whose derivative is x to the negative 3/4 smaller? Yes, indeed. So I take as a guess x to the 1 over 4 plus the obligatory constant c. And when I check it, then the derivative of x to the 1/4 is exactly what I hoped it would be. 1/4 times x to the minus 3/4. Yay! They kind of set it up for me like that. Okay. Now, this is the general solution. All functions who have a derivative of 1 over 4x to the 3/4 will be in this form. Now, what does this mean? If I were to draw a graph of some of these, if I let c equal 0, I would get y equals x to the 1/4, which looks something like that. So this is what the curve looks like when c is equal to 0. If I let c equal 1, then I would get y equals x to the 1/4 plus 1. If I let c equal 2, like so. You guys remember your transformations, right? And so you can see that this plus c is just going to be a vertical shift, either up or down. So that this actually represents an entire family of functions that differ by a constant. They are parallel curves, because they have the same slope. And one, and only one, of these curves is going to go through the point 1 comma negative 2. So visually, what I want to do is to take my curve y equals x to the 1/4, and I want to pull off a transformation down until my curve locks in to this specific point right here. Now it turns out that that's algebraically really easy to do, because since I know a y value and since I know an x value, all that I have to do is to substitute the y value and the x value and solve for c. And since 1 to the 1/4 power is 1, therefore I get c equals negative 3, so that it turns out that when c is equal to negative 3, then this member of the family goes through the required point 1 comma negative 2. So in order to find the value of C that we're looking for, we need one piece of additional information, which is a point. I want you to think about another thing that we've often done, which is to find equations of lines, right? And when we have, when we need the equation of the line, what two pieces of information do we need? The slope and a point. Now suppose I gave you only the slope. Give me the equation for a line with a slope of 3. Well, you would say its y equals 3x plus something, but you don't know the something unless you know one point that the line goes to. Here, I have given you a slope for a curve, and that allows you to say that that curve is equal to x to the 1/4 plus something. But in order to find the something, you need a point. Okay, let's look at another one. Let's consider number 37. And here we are told that f prime of x equals 1 over x plus 2. And we have an interesting little domain thing going on here with x greater than -2. And we are told also that this goes through the point -1, 3. Okay, talk me through the process of finding the f that I'm looking for.
First out
There you go. It's going to work just like this. Okay. Now we need a solution. Function whose derivative is 1 over x plus 2.
the ln.
Now, what are you forgetting?
Oh,
Plus it, right. Now, he's not sure about his function. What does he need to do to become sure? Check it. Check it for me. What is the derivative of L under x plus 2?
1 over x.
There you go. If it has the right derivative, it's right. Okay. Now we need to find the point, the value of c using the point, and since f of x is equal to 3 when x equals -1, you can plug in. What is the natural log of 1? It is indeed. So that c is equal to 3, and I have my function. And so we're happy with this. But now we wonder about that domain. Let's come back to the domain and see why this domain was necessary. Well, if I look at the curve y equals natural log of x plus 2 plus 3, you can see that that is going to be a transformation of f of x to the left by 2 and up by 3. So that I can take the vertical asymptote for ln x, shift it to the left by 2, and shift the entire curve up by 3, so that my curve is going to go through the point -1. And then here's my graph. What do you notice about the graph? Its domain is for x is greater than -2. So that when I take the derivative of this function right here, the derivative is only valid for the places where f is differentiable, namely for x is bigger than -2. So the reason we had to include this domain was not so that we did anything with it, but in order to specify that in fact f prime is 1 over x plus 2 only for x is bigger than -2. And so that the problem would be accurate and complete, rather than so that we would do something with it. Yes?
Well, we know what type of
Actually, it's because the function is not continuous. It doesn't exist for x is less than or equal to -2.
I mean, what type?
Yeah, its type is non-continuity. Remember that whenever f is not continuous, it can't be a function. Okay, here's one for you to try. Number 38. F prime of x equals 2x plus 1 minus cosine x. And it goes through the point 0, 3. You guys go ahead and find f, and we'll be right back. Okay, what you got? Do you have a representation? What is it? Huh? That you need to tell me first.
Yes.
Yep. Okay, now.
X cubed plus x minus plus c.
Yes. If you do not have the plus c, it will not go through the right point. Okay, now find the value of c for me.
X
Mm-hmm.
and
Equals 3. Put a sign of 0. So that c is equal to 3. Yeah. So that c is equal to 3. And we put it all together. And that's it. Yes. Sure. Yes, sure. Jason has a question. He's going to demonstrate it up over here, and then I'll copy it over here. Right, the derivative of natural log of x is 1 over x.
So this one and this
Mm-hmm. Yep. And we're going to have to treat this one really carefully because this is true when x is greater than 0, because the domain of natural log is x is greater than 0, but the domain of 1 over x is larger than that. So we're going to have to deal with negative x's carefully, and we'll do that in days to come.
So it could be different the other examples.
Yes, it's actually going to end up being the natural log of the opposite of x.